Hi guys, welcome to yet another MDE paper of the week. This week we're going to look at a Groher and Voelter paper using aspects to model product line variability. Before I get into the paper though, I'd like to have a quick discussion about a tool that I found recently. It was mentioned in my university's forums and I found it to be extremely useful. I mean, if you're doing a PhD like mine, that's actually a little bit open-ended, where you need to read a lot of different things and trying to understand lots of different bits of information. One of the problems you're going to end up finding is finding the right papers. And I think computer science is probably a classic case where this happens quite a lot. You need to you wander a bit until you find what you're looking for. And so this tool called Connected Papers is absolutely amazing actually. What it does is you put in a paper. For example, I've put in using aspects to model product line variability, and it builds a graph of all the related papers. And then you can see here in the graph, it contains quite a lot of information. So it gives the color tells you how far back in time the paper is in this range. So the darker papers are the most recent ones, and the size of the circle tells you how relevant the paper is. Now I don't quite understand exactly how these measurements are made, but it seems to work fairly well. You can of course zoom into the graph and mess around with it a little bit. And then you could choose the papers and have a quick look at the abstracts just from here. And if you find something that is of interest, like for example, this paper here is a very interesting paper, which is just a little bit big, so we haven't actually reread it yet. But let's say we find this is an interesting paper, we can just click on that. And it will take, because all the papers here are papers from the archive and other open sort of journals, I guess. You can access the, just as I say that, this one isn't in archive. But in most cases, the papers are in archive, and you can click on here and just obtain the contents of the paper. So I'll just use it as an example, the current paper that we're reviewing. And you can just click on the view PDF and away you go. Here's the paper. So I think Connected Papers is an absolutely amazing tool, and the people that are behind it should really get huge amounts of kudos, I think. So now let's just go back to what we're actually supposed to be talking about, which is the Groher and Voelter paper. Now Voelter, you probably remember, is the chap that wrote the book, the model-driven software development book that we talk a lot about. Iris seems to be a colleague at the same university. So the abstract of the paper then, the often cross-cutting aspects, characteristics of feature implementations make effective variability management a predominant engineering challenge in software product line engineering. Features can often hardly be modularized, but are spread over several other modules. In this paper, we propose XWeave, an approach that facilitates variability implementation, management and tracing by using aspects to model product line variability. In our approach, we use models to describe product lines. Aspect-oriented techniques are used to help implementing the variance in the models. We argue that due to the fact that models are more abstract and is less detailed than code, variability on model level is inherently less scattered and therefore simpler to manage than traditional variability management on code level. Okay, so all this makes perfect sense. Now let's just find a bit here that are more important than others. So I think this is quite an important point. It is quite tricky to manage variability. This is one of the biggest problems we all find whenever you're doing MDE. You really struggle to manage variability. I mean, one of the reasons why we try to keep variability to absolute minimum is exactly because of that. And then the second point here is features can often be modularized but are spread over several other modules. So this is also a very important point, and I think here we probably should go for a red, because this is another thing that we are extremely concerned about. Let's do the usual dance of the colors and see if you can get pink. Oh, this takes a couple of goes. Seems like Emacs is warming up a little bit. In this paper we propose XWeave, so that's just their implementation. We don't really care too much about those details. An approach that facilitates variability implementation, management and tracing by using aspects to model product line variability. Now, do you perhaps care about the rest? So, you can just basically say this. In our approach, we use models to describe product lines, okay? So do we? Aspect-oriented techniques are used to help implementing the variance in models, okay? We argue that due to the fact the models are more abstract and less detailed than code, variability model life is inherently less character. Okay, this is a very important point. She's not really tightly coupled to the implementation. So we probably should go for maybe green. Must say we don't really have much of a color scheme, but since we highlight so much, we do need colors. Let's just have a look at what they have to say for themselves then. Software product line engineering, SPLE, aims to reduce development time, effort, cost and complexity by taking advantage of the commonalities within a portfolio of similar products. Fairly standard definition. Products usually differ by the set of features they include in order to fulfill customer requirements. A feature is defined as an increment in functionality provided by one or more members of a product line. Again, I feel a little bit bad for highlighting so much, but of course all these things are useful. The effectiveness, well, perhaps we should put a note here. Product line engineering. Let's put a couple of points. Actually, one thing we did not do was to capture details of the paper. Let's just have a quick. Actually, I do find that it's easier to just go to Scholar when you're trying to capture details of the paper. To be honest, maybe just a lazy part of me. I normally just tend to either obtain this bit here or the bip tech, which seem fairly straightforward. If you put the link to the paper here as well, we use these later when we are writing the video details. Now then, so SPLE takes advantage of commonality between products in a family to reduce, or perhaps to improve reuse and but largely to improve reuse, I think. That's kind of what we're trying to say here. Products in a family differ from the features they have. Features are increments in functionality. It's always standard stuff, but it's always good to start writing these things down, make sure they stick. The effectiveness of a software product line approach directly depends on how well a feature variability within the portfolio is managed from early analysis to implementation through maintenance and evolution. Okay, in our particular case we care really mainly about maintenance and evolution. Those software product lines aim to simplify software development and improve reuse by managing variations of a software across different operational contexts. They themselves tend to be quite complex. I know we're highlighting a bit too much here, but sadly these are the papers that seem to have a lot of points to make, a lot of interesting points. Variations often have widespread impact on multiple artifacts in multiple life cycle stages. This is very important, making the effective management a predominant engineering challenge in the SPLE. Now, what are we trying to say here? Let's try to move more towards our world. So what are they saying? Let's imagine you're trying to create a product, and let's imagine that Dogen supports everything for SPLE. When you create a product, you can choose things like whether you're supporting Travis, for example, or whether you're supporting, say, GitHub Actions, or all sorts of product lifecycle options. As you enable and disable these things, Groher will generate different bits of code. So for example, if you decide to enable Travis, we need to generate the Travis YAML file, as then they're going to tell Travis what to do in terms of the build. So we're saying there is variations, which CI system you're using, must be captured somewhere in the model, and then depending on what knobs you've enabled or disabled, the code generator will then decide what to do. The problem, of course, is that these things don't just come alone. They don't come. You don't just have one knob that influences one thing. The knobs then have a cascading effect, because when you enable Travis, perhaps then there is a deployment, say, that then goes into Bitbucket, or not to Bitbucket, but to bin tray, as is the case with Dojo. And then let's say that you then need some further configuration related to bin tray. And for the sake of an example, let's say that that configuration does not live in the Travis YAML file. And in reality it does, but let's say it doesn't. So then what we're saying is that this one feature will then have a knock-on impact on multiple elements that are being modeled. And of course that's a really simple example, but there's other examples, particularly the way they are modeling things, where you could enable things at one level and then suddenly there's all sorts of things that get touched because of that. And so this approach requires a way to manage this sort of cascading effect, and that's kind of what we're saying here. So, for example, variations in the persistence or security policies employed by products in a product line can have a wide-ranging impact on the different kinds of artifacts, from requirements to test specifications. Their problem is even worse, because they're not just focusing on the implementation level, they're focusing on a complete life cycle, whereas we at least don't have to worry about that. They also are spread over multiple assets within one artifact type, i.e. they cross-cut, okay, this is very important, they cross-cut various requirements, documents, design, code, and test artifacts. Right. We have already encountered this. So for example, if you enable certain features of an object, then the tests, the generated tests, then have to take that into account. So our variability has already gone to that level now. Despite their crucial importance, so perhaps this should be a red really, because it's more of a warning thing. It's a problem rather than a... Despite their crucial importance, feature implementations are often hardly modularized, and there's only little support for incremental variation of the feature functionality. The reason is that feature-specific parts are often cross-cutting nature. This means that features can hardly be modularized but spread over several other modules. So, I don't really want to highlight the entire paper, but sadly so many interesting points being made here. Sadly, this is not the first time we read this paper. This is a very good paper, and it's really it's been quite influential. In traditional SPLC approaches used in the industry, variability is mainly handled using mechanisms provided by the implementation language, such as polymorphism, reflection, patterns, frameworks, and precompilers. So if you think about it, this is talking about traditional coding, right? We're talking about the configuration files and any other sort of aspects that one may use. Okay, seems like I've been called. 1 second. So in traditional SPLC, so these are basically the traditional means that we normally use for coding variability, code level. Additionally, configuration build tools, okay, so now we enter the config files, are used to set compile time variables and select variants of assets. On the implementation level, often preprocessors are used to write feature-specific code fragments in if and if statements. So this is the classic sort of Linux kernel sort of approach. Our approach integrates model-driven software development and aspect-oriented software development into product lines to facilitate variability implementation, management, and tracing from architectural modeling to implementation. So they're putting forward their approach in contrast to the traditional code level approaches. We argue that due to the fact that models are more abstract and is less detailed than codes, variability on the model level is inherently less. So this is basically a point we already highlighted. Less scattered and therefore simpler to manage. I will highlight this point again, sadly, because I think this is quite a crucial point. We are recording, so because we have exactly the same point in our approach. Managing variability in the model is a better way of doing things. Perhaps we could put a note here too. MDE, SD, and expert-oriented SD. The authors put forward a merge between these two approaches as a way to manage the entire life cycle of variability, as well as dealing with the cross-cutting nature of most features. Okay, they also argue that moving to a model level abstraction permits less scattered, how do we say less scattered? More compact, and therefore more manageable view of variability. This is clearly the case, right? I mean, we've already experienced this in Dogen. I mean, the fact that, so if you just jump over to a Dogen model, the fact that we manage variability at a high level, the fact that we can just turn on knobs here, allows us to very quickly, and particularly when we start making use of things like profiles, I can switch on and off very, very high level things, such as, for example, I don't know, the type of license that I use on the files, or you know, whether certain aspects are enabled or disabled. And doing this at such a high level enables us to do it in a much more sort of manageable way, rather than having to go through lots and lots of files and so on. This is clearly a point we've already experienced ourselves. Variability can be described more abstractly, since in addition to the traditional mechanisms, e.g. pattern, frameworks, polymorphism, variability can be described at the level, on the level of models. In this paper, present X-weave. Weaving, of course, is an aspect-oriented term. A model weaver that allows to describe features as aspects. The aspects can be composed with so-called core models representing the commonality of the product line. So this is an interesting point. Additionally, we integrate the variant management tool, Pure Variants, into our tool suite to be able to perform the weaving based on current feature selection. The remainder of the paper is organized as follows. So section 2 presents the X-weave approach and illustrates how aspect models can be linked to the configuration models. Section 3 discusses related work, and section 4 summarizes the paper with a note on feature work. Now, we've chosen, of course, to read this paper because it's only 8 pages long, whereas the paper that I mentioned, as I was saying here on the connector, the 2008, this chap here, 2009 paper, is much more extensive. It just basically provides a lot more details, but the crux of the argument is made here, and also this is available in archive, so we don't have to worry about paywalls, which is a criteria for all of our papers. Of course, I can access all the papers via the university, but I think it's a test, really, whether you can develop all your work without having to have access to the paywalls. So then, modeling features as aspects. When expressing variability in models, additional model elements have to be connected to the core at specific points. There is similarity in to the concept of joint points in aspect orientation. In AOP, joint points are those elements of a programming language semantics which the aspects coordinate with. In modeling, joint points are elements of the modeling language which aspects coordinate with. And in product lines, variation points represent variability subjects within domain artifacts. Domain artifacts must include all kinds of development artifacts. Right, so first let's just capture this bit here because I think this is relevant. I mean, I'm ignoring slightly the aspect-oriented bit there. Domain artifacts include all kinds of development artifacts such as requirements, architecture, design, code, and tests. The similarity in the concept of a variation point and a joint point makes AOM and specific, obviously aspect-oriented modeling, and specifically model weaving well suited to candidates for implementing variability in structural models. Okay. Similar to weaving codes level aspects in traditional aspect-oriented languages, aspects are often defined in model level and are composed with a base model. So, I mean, obviously, just to explain what they're trying to say here, there are two models. One model which is the base model, and then the second model which contains the aspects side of it. And then they need to be weaved together. As if the reason why they weaved is because you're kind of joining the two things together. Similar to weaving of code level aspects in traditional aspect-oriented languages, aspects are defined at model level and are composed with a base model. Weaving is technically done by an aspect weaver at designated joint points. An important advantage of using aspects to implement variability on model level is the fact that models need not be prepared for variability in advance. Aspects encapsulate the feature implementations and can be connected to a base model at desired points. In traditional approaches, models need to incorporate all variability that is inherent in the product line. Hence, using aspects to implement variability is more flexible than adding explicit variation points to models. Okay, this is a very good point, and we must say that in our case we are on the less flexible side of things. Right, so we take the exact opposite approach here. Variability requires preparation. Aspects of variability increases flexibility. By using aspects, the model does not need to be prepared for variability in advance. We take the contrasting. We only support very limited cases of variability, and these must be exposed explicitly. Our approach is by design less flexible. Right, where are we then? Model weaving assists in the composition of different separated models into a consistent whole. It allows us to capture feature-dependent parts, of models in aspect models. So perhaps this is worthwhile highlighting. This technique supports a clear separation of variable model parts from the core and supports an automatic composition to create a complete model representing a member of the product line, presumably. Yes, a member of the product line. Of course, there is a lot of similarities between what we're trying to do here and the projections across physical space. Except where they use aspects, we choose a coarser-grained approach. So I think what we should probably say here is comparison between our approach and aspects. The multi-dimensional approach put forward in Doge also is overlaps and extend the aspect-oriented modeling approach for variability in the paper. However, we focus on coarse-grained I hesitate to use the word aspects here, but features maybe, and we don't provide flexibility, and composition is only allowed under very narrow or in very narrow circumstances. We need to provide a review, a comparison of both approaches. It's quite an important thing, really. So, this should probably have been green. This technique supports the clear separation of variable model parts from the core and supports an automatic composition to create a complete model representing. Okay, right. I would like to also highlight this bit here, because I think we also provide this with our approach, which is different but similar. However, we also have a clear separation of the model elements and the variability modeling. Okay. During domain engineering, the core model and so domain engineering, for those less familiar with, is the approach where we have the application engineering, domain engineering, and during the domain engineering we're kind of basically trying to make sense of the domain itself, and then the application engineering is the instance of what we've learned in domain engineering. So during domain engineering, the core model and the aspects are developed. The core represents model parts common to all products in the product line, and the aspects represent features that are increments in functionality necessary for one or more members in the product line. During the application engineering, so this is the second phase, the aspect models are composed with the core according to a selection of features in the configuration model. So this is exactly the approach we have here. So domain engineering, application engineering. Dogen uses the exact same approach as DEAE, except the DE portion of the work is related to the development of Dogen itself, and the AE portion of the work is the application of Dogen to user projects done via configuration. I'm not entirely sure why this note is here. Oh, it's probably because it's to do with the height of the page rather than the actual where it is in the text, if you see what I mean. Consequently, the core is minimal in that only contains elements common to all products. Well, actually, sorry, before we go any further, I think yet again we need a large highlight here. This perhaps can also be green. I mean, some of these highlights we're just basically saying, okay, this is something we read and it's interesting. Consequently, the core is minimal in that only contains elements common to all products in the portfolio. Product-specific parts are added when needed, in other words, by switching things on and off. This section demonstrates XWeave, a tool that supports the expression of variability on meta-model and model levels. It's based on Eclipse. This is a classic Eclipse melding framework stuff as a tool platform, and eCore as a meta-meta model. Since it's an OAW workflow component, it is integrated into OAW model processing. Xweave is a model weaver that can weave models that are either instances of an of a core called meta models, or instances of these meta models called models. The tool takes a base model, so you must already start to see what they're doing here. The weaving is happening at the model level. So I should grab a bit of water. What we're saying at the moment is that we're going to weave the model elements. This is something that we very much are against. Our weaving, and that's why we put forward our approach. So again, probably should put a note here. Model level weaving. The approach put forward results in the weaving of model elements, something we are avoiding by design. It increases the complexity of the modeling process quite a lot, as it increases. I'm sure that Groher and Voelter would disagree with me, but this is our view. The tool takes a base model. Yes, so there we are. So let's just read this again. The tool takes a base model as well as one or more aspect models as input and weaves the content of the aspect models into the base model. So as an example, sorry, I meant to say Ctrl-C, Ctrl-H. So as there's an example where you can imagine is you have a model that has something like, I don't know, say logging aspects, and then another model that has the base model, and then if you've enabled logging, then this weaving will now join the two things together and add model elements related to logging. So weaving an aspect means that all properties, exactly what this is about to say now. Weaving an aspect element means that all properties of the element, including the child elements, are woven into the base model. Both aspect models, actually, interestingly enough, we do support a form of weaving, which is via. So we probably should put a point here somewhere. In fact, to be honest, perhaps we could just use the model level weaving. We need to compare and contrast the weaving that is performed by object template configurations against the weaving of model elements proposed by this paper. Because we are doing a form of weaving, really, it's just that our weaving is a bit different. And besides, it's not really that optional. I mean, you choose some, so as an example, let's just have a quick look. Say you choose, say we take the logical model, for example. Say you define a concept like, say, associatable, for example. And then you just use that as part of your stereotypes, and then we just weave all of the properties that come from that tree of object templates onto the object that is making use of it. So it's in a way, there's similarities there. Weaving an aspect, so both aspect model and base model must conform to the same meta model. The aspect model consists of definitions that capture the points where in the base model the additional model elements should be added. Right, so this is the point where it enables you to do this generically. It also contains these additional model elements, the advice in AO terms. This is the form of asymmetric AO because the aspect model is not complete by itself, but enhances a given base model. Okay. During weaving, so it seems like we lost our soundtrack. Afraid I quite like to program with music. So look if some FM just died on us. Oh well, let's proceed. Seems like we've lost it for today. So there's an asymmetry going on here. This is the form of a symmetric AO because the aspect model is not complete by itself, but enhances a given base model. Okay, there's two, as you can imagine, there's two different kinds of models. During weaving, aspect elements are physically woven into the base model. The result of this process is an updated model. Subsequent tooling cannot tell the difference between a woven and a non-woven model. I'm going to highlight this because this is exactly we should use weaving terminology. For these terms, we also should mention that after weaving, you cannot tell that weaving took place. Might be a relevant thing. The joint point model, how are we doing for time actually? Just keep an eye. 35 minutes. The joint point model of XWeave is purely based on the meta model of the base model, and thus generic. All elements of the base model are potential joint points. This means that any model element of EMF model can serve as a joint point. Okay, it's flexibility. Point cuts select those elements where additional elements can be attached. XWeave provides two ways of specifying point cuts: name matching and explicit point cut expressions. Now we're going to get into the machinery of this, which is slightly less relevant for us. The next section will introduce both approaches in detail. So let's have a quick look at this. Presumably the name matching is just going to be what we are used to into programming terms, some sort of matching. It's not going to be particularly complicated. Name matching means that if a model element in the aspect model has a corresponding element in the base model, both name and type have to be equal, the elements are combined. Hence, matching happens purely based on name and type equivalence. The device elements defined in the aspect model are added to the base model at the matched joint points. Figure 2 shows an example of name matching XWeave to specify the desired joint points. It is an application of meta model weaving. The model in A shows the meta model of a simple state machine. The state machine has a list of states linked by transitions. The meta model only supports simple states. A variation of this meta model is to not only support simple states but also dedicated start and stop states. The model in B illustrates the aspect model. Start state and stop state are derived from state and should be woven into the base model. The aspect element state has a corresponding element in the base model and is therefore the point at which start state and stop state are added. The model C shows the resulting model weaving. It should be quite straightforward. So there we are, the start state, the stop state, all part of state. The base model has state here. As you can see, they look more or less identical. The weaver kicks in, and then the result. Oh, actually, sorry, we just skipped a step. This is the result. So start state, stop state, state is there, and then after weaving, you see that the model now ends up with 3 descendants of states. The point cut expressions. Another way of specifying point cuts are explicitly point cut expressions. They can be defined using OAW expression language. Expressions can select one or more elements of the base model and are defined external to both aspect and base model in a separate expression file. Every expression has a name. The named expressions, point cuts, can be used in the aspect model. If an aspect element name starts with %, dollar, or question mark, followed by the name of a defined expression, the expression will be evaluated for this element. In the percentage sign prefixes an expression that returns a collection of elements. The dollar character marks an expression that returns a single element, and the question mark character is followed by a string expression, i.e. it has to return a string. It can be used to add strings to elements. Additionally, it is possible to use the asterisk character instead of the name of an element. This matches all instances of that particular type of the element. Point cut expressions make it possible to select several joint points on the model with only one declarative statement. Now, of course, there's a lot of complexities here to do with their own implementation. We don't really need to know this in quite detail, but you can see that they're trying to come up with a really, really flexible way of doing the joining of the two models. It's very clever, of course, but this is the sort of thing that we are trying to kind of run away from, because you can imagine that you need to really know what you're doing for this to work very well. Particularly if you take as an example, I mean, Dogen is still a very small project, but we already have best part of, I don't know, 10 models perhaps. Some of these models are becoming quite large. So if I just give you a quick, this is just a logical model, and you know, there's a lot of complexity going on here. There's models like the text model, for example, which is where a lot of the work is going on at present, which are probably even more complex in some ways. So you can imagine that once you start introducing something like aspects to the mix, and once you start having regular expressions, you start entering this JDSVZ problem. I mean, you start with one problem, you end up with probably more than one. So this is very clever, but it is difficult to use in practice for those that have actually experimented with sort of things. So point cut expressions make it possible to select several joint points in the model with only one declarative statement. This is referred to as the quantification principle of AO. Expressions must be parameterized with the type of the element that serves as the root for the base model. Whatever the expression returns will be used as a target for the weaving purposes. To express point cuts, XWeave uses the OAW expression language, which is a syntactical mixture of OCL and Java. A complete reference of the language can be found in 20. Figure 3 illustrates the example of a point cut expressions. In A state machine model of an oven is presented. Also note that they're focusing a lot on state machines here, whereas we don't have any support for those. It is an instance of the meta model presented in figure 2. The oven can be either open, closed, or in cooking state. The aspect models in B and C weave an emergency state into the base model, including the respective transitions. The aspect model in B uses a point cut expression to select all states of the simple state of type simple state using the point cut expression PC. The aspect model in C is an alternative to using the point cut expression. The asterisk matches all the instances of a particular type, in this case simple state. The model in D shows the result after weaving either the aspects shown in B or C. Figure 4 presents a snapshot of XWeave. In a meta model of a state machine, in A meta model of a state machine is illustrated. A state machine can contain different kinds of states, namely start states, stop states, and simple states. Transitions indicate state changes, and actions are performed when entering or leaving a state. In B, a state machine model of an oven is presented that is an instance of a meta model illustrated in A. Now, as you can see, I'm kind of skimming through this a little bit because I'm not really particularly worried about the exact details. So we got some typical pictures of Eclipse with EMF, and this is basically showing the views that I got of the state machine and so forth. The aspect model corresponding to the one presented in figure 3b is shown in figure 5. It weaves an emergency state. Well, of course, if we were looking at this more carefully, what you probably would see is, as you can see here, the states being woven, and you can see, for example, the simple state and so on in the different figures. It weaves an emergency state, a stop state, and the corresponding transitions to the other model in figure 4b. The point cut all states selected selects all elements of type simple state in the other model. It is defined in an external expression file that contains a named expression corresponding to the point cut name. Now, I don't particularly like the fact that they're using external expression file as well, because as we've seen in Dogen, it just makes things even more complicated. Figure 6 presents the result of the model. The states emergency stop and stop state and the transition stop and emergency have been woven to the oven model. Note that the state open now contains an additional out transition emergency. So this is the result of the weaving. And AO systems aspect precedence is an issue, i.e. the advice ordering in case more than one advice is applied, yes, at the same joint point. So you see the complexity I was mentioning a second ago. Now, if we have more than one match, depending on the order which we do the matching, we may end up with the model being woven in one way or being woven in another. And we may even start creating dependencies of the weaving. So this is, I mean, I'm going to mark this as red because I think this is exactly what we're talking about when we mean the complexity of these kind of processes. It's not to say that I'm against them. I think it's very important that people are experimenting with these things. It's just that that's not what we're trying to do with Dogen. So we need to read about these things, but we need to filter them, get the ideas that are relevant for us. Woven models can thus be an input for subsequent weaving processes, as XWeave does not distinguish between a woven and non-woven model. Again, think of the complexity of this. The variant management tool PureVariant has been integrated into OAW to support seamless and efficient model-driven aspect-oriented product line engineering. So we selected PureVariants because it is an industrial strength tool that is well integrated into the Eclipse platform. PureVariants is a variant, so what is it? A variant management tool that manages product lines and assists in producing individual model variants, individual product variants. The basic idea of pure variants is to model product lines with feature models and family models. Probably want to keep this as well. The problem space is captured in feature models and the solution space is captured in family models, separately and independently. This is relevant as a requirement for our approach. A feature model lists the features of a product line and specifies the interdependencies between those features. They represent all variability and commonality of the products in the product line. A family model, I think we are highlighting a lot here, but consists of so-called components. Components represent elements of the software solution and contains parts like classes. Okay, right, so I think probably all of these. Further, the relations between feature and family model are described. Features can require or prohibit the inclusion of family model elements. Pure variants also supports the use of multiple feature and family models that are hierarchically linked. Users can select features required for the desired product from the feature models. In pure variants, a selection of features is called a variant model. Pure variants checks the validity of the selection and, if necessary, automatically resolves dependency conflicts. A valid selection triggers an evaluation of the family models that contain component definitions consisting of logical and physical parts. The evaluation process results in an abstract description of the selected solution in terms of components. Within the OAW tooling, a pure variant model is used to describe the global configuration of the product line. Such a global configuration model can be queried, and hence MDE activities can be performed based on the selection of features. Workflow components, model transformations and code generation templates can be linked to features, so this is extremely flexible. Their execution depends on the presence or absence of features in the configuration model. So, the data transfer between pure variants and OAW is done using EMF eCore. An automatic variant model export has been integrated into pure variants. An EMF model that conforms to a defined meta model is created by pure variants. It contains the set of selected features. The OAW runtime reads this model and makes the variant information available for querying by OAW workflows, model transformation functions, and code generation templates. Now, I don't want to harp on too much about the complexity of all of this, but you can already see how it requires a very large mental model to keep track of everything that's going on here. I mean, I understand what they're proposing, but what you have to bear in mind is, in a realistic system, where you're probably going to end up with dozens of models, and where all these models are configured by other models, and the switching off of knobs triggers cascading operations across the entire model stack, it will be extremely difficult to keep track of all of this. And so you really need very good tooling in order to be able to use this in production. When using XWeave, the dependency between aspect models and features is specified in the OAW workflow. Aspects that implement optional parts of structural models are linked to features defined in configuration models. Based on selection of features, the corresponding aspect models are woven into the base model. The dependency between features and aspect models is illustrated in figure 7. So, a very simple figure. Listing 1 shows an example workflow. Now, if you are keeping track of where we're going, we now have a workflow that's built on top of all of this that's going to define the steps. And this is not exactly trivial. If the emergency state feature is present, in the global configuration model, XWeave weaves the content of the aspect model into the oven model. Aspect and base model are illustrated in figure 3. The base model is assumed to be already in a workflow slot. XWeave only supports additive weaving and is clearly an asymmetric approach, as there is a clear distinction between aspect and base model. I think that's fair enough. In SPLE, typically a core capturing the commonality within a portfolio of similar products can be identified. Features are increments in functionality and thus match well with the idea of an asymmetric weaving. However, in contrast to most asymmetric AO languages, it is not possible to remove, change or override existing base model elements. Okay, they seem to be very impressed about this, but the base is the base, you can't go any less than the base. A clear advantage of XWeave over existing model weavers is that woven models can be input for a subsequent weaving process, as XWeave does not distinguish between a woven and a non-woven model. Further, the weaving process is strictly sequential, and the developer specifies the aspect precedence directly in the workflow file. The fact that one can actually look at the woven model has a positive impact on understandability and reusability. With that, I agree. We should always make all the steps available so people can understand what the tool is doing. Related work. The Atlas Model Weaver AMW is a tool created as part of the Atlas Model Management Architecture. Its primary goal is to establish relationships between elements of different models which are stored in a so-called weaving model. This process can be done manually or semi-automatically. Based on a weaving model, one can generate model transformations that merge models. AMW is similar to XWeave that both tools can weave or merge models. There is, however, an important difference. AMW does not support a joint point model. It provides an interactive tool to build weaving models, whereas XWeave, okay, let's just highlight this. So they're basically continuing to highlight the fact that their model is extremely flexible. You don't need to know where you're going to join things together. It's completely flexible, whereas not the case with this AMW. Seesaw uses a general transformation engine for manipulating models based on aspect specifications using ECL, a variant of OCL. The weaver traverses the model and selects a set of elements to which the aspects should be applied. The device then modifies the selected element in some way, for example by adding a precondition or changing the element structure. Seesaw has been developed to tackle the challenge of evolving large models in a consistent way. Instead of applying a set of changes manually, one merely writes an aspect that applies the change to all selected elements of a model. Okay, again something very clever. Comparing to XWeave reveals that Seesaw does not weave models in the sense of merging them as XWeave does. Rather, efficiently applies cross-cutting changes to a collection of elements in a large model. The Motorola Weaver is a model weaver developed as a plugin for Telelogic Tau. It supports weaving UML straight charts that include action semantics that are executable. There are two different types of joint points, action and transition joint points. Advice is encapsulated into a construct called a connector. Similar to XWeave, the Motorola Weaver weaves aspects based on point cut specifications. The main difference between the two approaches is that XWeave provides a generic EMF-based solution that can weave arbitrary models and meta-models. The Motorola Weaver only supports weaving of UML state charts. Generating AOM approaches are also related to XWeave. A theme UML, for example, provides an extension to UML that supports concern modeling and composition. Most AOM techniques are based on UML, which is an important difference to XWeave. So what they try and say here is because they are one level up in eCore, their approach is more flexible. Also, most approaches are like tool support, which is essential for a successful application technique. So here I think this is really probably the most important thing that's been said so far. The tool support for this is quite decisive, really. You must have an extremely good tool to manage all of this, and even then it will be still quite a difficult thing to do. Summary and future work. Typically, in model-driven product lines, domain-specific languages allow one to describe structural variability. By this, different models can be created that vary with respect to the model elements they consist of and relationships amongst the elements. The implementation of feature-based configurative variability was not supported in current modeling approaches. Our approach contributes to this by providing concepts and tools that support the implementation of variability on model level. And then perhaps we should highlight this as their approach. We utilize aspect-oriented concepts to express how a feature described on model level is attached to a minimal core. Our approach works on model as well as meta-model level. In existing tooling, it was not possible to define configurative variability in a global feature model and make MDST steps dependent on whether certain features are selected in a current configuration or not. Our approach contributes to this by providing means for querying configuration models created pure variants from within OAW. So this is something we're not particularly interested in. An implementation direction for future work is the improvement of the tool suite we provide. First, a better visualization of the dependencies between artifacts and features is necessary. For example, workflow components that depend on a certain feature will be highlighted in the same color. We currently only support querying of variant information for pure variants within workflows. Other variant management tools such as gears could easily be integrated into our toolchain. Also, we currently focus solely on the feature modeling to describe configurative variability. There are other important aspects such as decision-oriented approaches and orthogonal variability modeling. Their integration is another important future research direction. Further, XWeave currently only supports additive weaving. In the future, XWeave could be extended in order to support changing or overriding existing base model elements using aspects. Another possible extension of XWeave is to support symmetric model weaving. Symmetric weaving does not distinguish between aspects and base models. Models are woven together according to defined rules to form the final system. Alright, so here we are, just the best part of an hour. Now this is a complicated paper, and it has some relevance to what we're trying to do, but the relevance is a little bit on the sides, if I could use that as an expression. In other words, we are proposing an approach to solve some of these problems, but our approach is not aspect oriented, and we don't weave in the sense that they propose here. So what we need to do is to make sure that when we are proposing our approach as part of our work, that we clarify the differences between an aspect-oriented approach versus a multidimensional approach of managing the variability and the weaving. So this will be a contrasting, compare and contrast kind of paper in the final scheme, in the final picture that we're trying to build. And nonetheless, it was a very useful paper. Thanks very much for watching.